Hello and welcome, everybody, to this U of Care podcast. My name is Oliver Grundmann, and it is my pleasure to introduce and talk to Dr. Clint Stober today. Dr. Stober, do you mind introducing yourself?
Yeah, sure. It's great to meet you, Oliver, and great to be on your podcast. Yeah, my name's Clintin Davis-Stober. I'm a professor of psychology at University of Missouri. I specialize in mathematical psychology, quantitative psychology. So, said simply, I use mathematics to describe human behavior, which is kind of as hilarious as that sounds, or as futile as that sounds, but it's a lot of fun. I specialize in decision theory in particular, like how people make decisions. Can we put mathematics to that? So, like, I collaborate with economists and these sort of people as well, but like, kind of my core interest is can we understand how people make decisions, and then how can we make better decisions? And then I also have lots of methodological interests. So all along those lines.
That is fascinating. Mathematical psychology sounds like two things that you do not think naturally would go together. But it's kind of interesting when you say it. I mean, when you look at it from a Vulcan logic perspective, I guess mathematics is at the core of logic processing, right?
Yeah, yeah, exactly. I mean, mathematical psychology, it's a field that's been around for a couple hundred years and it's sort of, or at least 150 some years, but it's very overrepresented in a sense. Like there aren't as many mathematical psychologists, but you definitely see their impact in the various areas of work. And yeah, and I guess at first blush, mathematical psychology doesn't seem like it goes together, but in my opinion, it's like peanut butter and chocolate. Like it goes very well together, unless you're allergic to either, and then not so much. But yeah, it's a small field, but we're out there.
That's exciting. I have never heard about it, to be honest, so I'm uneducated in that sense. So I would like to know what got you into this field, the kind of marriage of mathematics and psychology in your education.
Yeah, that's a great question. I guess to give kind of like a brief start at the beginning, my path into academia was very nonlinear, I guess one could say. I started out, I did an undergrad in journalism, and I worked in TV news for a few years right out of college. So I was an on-air reporter, I did photojournalism, I did some writing, and I worked at a couple different TV stations, which was it was a lot of fun. It was very exciting. But I kind of had a yearn for deeper questions or different kinds of questions. And so, long story short, I kind of started over in a sense and fell in with a attention lab. Actually, I worked with Michael Posner at University of Oregon, which was a wonderful experience working with him and Mary Rothbard. I got really interested in psychology. And at the same time, I was taking all these mathematics courses. And, I'm sure I kind of came to mathematics a little later than some people, but it's kind of one of those light bulb moments where you're in a calculus class and you're like, oh my gosh, this is really powerful. Has anyone used this before? And then you realize that, yeah, yes, people have used calculus for hundreds of years, and that's why we have all the technology we have. But anyway, so I was very interested in mathematics, and I was interested in psychology. And, while I was at the University of Oregon, like those two interests really started to gel. And then that kind of led to where I wanted to do my graduate work. And I fortunately discovered mathematical quantitative psychology. And so I ended up doing my PhD at the University of Illinois in quantitative psychology and earning a master's degree in mathematics along the way. And it was a very nice fit for me. I mean, the nice thing about mathematics is that, it's a language like anything, and it's a language of precision. And so we can really think carefully about the kind of behaviors, the kind of theory we want to instantiate, and mathematics then becomes like the language for that. And then along the way, my interests in testing and methodology just sort of evolved from that. So
It
that's
is
it's kind of long.
definitely. Yeah, but I mean, talk about nonlinear. I think we a lot of folks that get into the field that they really feel they belong in, they have a passion for, kind of have to figure that out because it's not something that you necessarily learn in a very structured setting, like in high school or even in your undergraduate college years, right? Because I mean, somebody who goes into mathematics might never look at psychology, and somebody who's in psychology might never look at mathematics. So getting these two together is kind of where to figure that out is it takes time, I would imagine. So when you say mathematics for predicting human behavior, what goes into that? Because is it just boiling it down to an equation, or is it more complex than that?
In some ways, it's like boiling it down to an equation, but I think it's first sort of starting with like the phenomenon you're trying to study and you want to understand. And maybe you can think about different experiments to probe this. And then you can think about how theory, like what a theory is. And I don't really have a good definition of what a theory is. I'm not sure anyone really does. But you can think about different ideas, different predictions, and the knowledge that you're trying to bring to the problem. In many ways, I want people to think of mathematical psychology as really just psychology. In that when we develop theory, when we try to make our ideas precise, mathematics is a great language for that. And, if I could just speak to all psychologists in the world, I would say, really embrace that mathematical structure because it allows you to formalize your ideas and make them precise, which in turn makes them even more testable, right? It makes very precise predictions, which allows you to develop very strong experimental and statistical tests of whatever it is you're trying to investigate. So yeah, I guess if that makes sense, like we shouldn't think of it as a niche thing. We should just think about it as part of this continuum when we try to develop and test our and evaluate our hypotheses.
So when I have other smart folks like yourself on this podcast, we often talk about factors that contribute to certain behavior or increase the risk of somebody developing a substance use disorder. And it sounds to me like that is basically one of the variables that is introduced into a mathematical model. And then at the end, because you can't account for everything, you kind of have this error kind of dummy variable, right? That accounts for the rest that you just can't account for in your model. Is that kind of how it could be understood?
One way to think about it is that you can think of all these different factors that you think may relate to an addiction phenomenon or someone's propensity to take a drug or something like this. And when you approach it kind of from a very quantitative mathematical way, you're trying to make a lot of things explicit. So for instance, maybe one of these factors is in a sense unobservable per se, but you collect measurements of it, right? And so there's a measurement relationship there. And the nice thing about the mathematics is that kind of makes that relationship explicit. Like, okay, we're using these survey items to measure depression, which is something that's in a sense unobservable, but we can use these variables to act as indicators of it. Well, then that kind of leads to other questions like, what is that relationship? Maybe it's nonlinear, maybe it's monotonic, maybe it has these strange relationships. And when all these different factors, like how they're combined to make this prediction about addiction, mathematics and these kind of statistical models allows you to make those relationships precise and allows you to say, okay, well, maybe this interacts, maybe this doesn't interact, but we can be mindful of these relationships and we can try out different functional relationships as well. And they may make different predictions, which in turn informs our experiments. It's just like kind of just part of a thought process, really.
Fascinating, absolutely fascinating. So, with that in mind, what is your current focus? What are you currently working on to contribute to our understanding and knowledge of human behavior, and specifically for addiction and substance use disorder?
Right. So there's a couple different things. So I'll talk first about kind of an addiction-focused line of research, and then I can talk a little bit about a more methodological line of research. So for the addiction line of research, I work with, my former postdoc mentee, Sarah McMullen, who's at Webster University now as an assistant professor, and my longtime collaborator at the University of Missouri, Dennis McCarthy. And we are developing models to help understand how people make risky decisions when they're drunk. And so, like Dennis's work, he runs an alcohol administration lab. where you bring subjects in, you can get them intoxicated, and then we can run various items. What's funny is I came to the addiction field almost quite by accident while I was an assistant professor at MU. I was running experiments on decision making that were not addiction at all. I was just trying to evaluate the robustness of certain decision properties. And I would try people to do it under time pressure. I wanted to see if they could still do it if they were stressed out. I wanted to see if they could do it under different complexity of stimuli on the screen. And I think Dennis and I were just hanging out in the hall, and I said, wow, it'd be really great is if I could somehow cognitively impair someone when doing this experiment. And Dennis is like, you know what? I got great news for you. That's exactly what my lab does. And I'm like, oh, yeah, okay, that makes sense. One study that we recently published just a year or so ago that I thought was very interesting is that we developed a decision-making model to try to understand how people make the decision to drive drunk. Unfortunately, people do make this decision on a fairly regular basis, and they do so while cognitively impaired. And what we were looking at were two particular decision factors that might influence how some might influence the decision to drive drunk. Now, of course, there may be lots of factors, but we kind of focused on two salient ones. On one, we looked at current consumption level, like how many beers had the person drank, like how many drinks have they had, how impaired are they? We've done different variations of this study where we actually got them intoxicated. We asked them based on this information, how you feel right now, would you drive drunk? So there's different ways of getting this information, but kind of at its simplest level, one factor is how much you've drank. The other factor we looked at was how much a safe ride cost. So this is definitely a factor people consider whether or not to take a safe ride home, is how expensive an Uber is or something like this. So in our experiment, which was hypothetical, of course, for hypothetical decisions, we varied the cost of the ride, like from a very cheap Uber ride to a very expensive Uber ride. And we developed a decision-making model that was very interesting in that it considered two types of decision makers. Someone who makes non-compensatory decisions in that they only focus on one attribute, or compensatory decision makers who used both attributes when making a decision. So the basic idea is you have someone who just ignores a piece of information and says, this is all I care about when I make a decision, and another decision maker who incorporates both sources of information. What was very interesting is that subjects were more likely to have reported drunk driving in the past 6 months when they made compensatory decisions. Now, what that meant was drink level, how many beers they'd had, would in fact influence their decision, but it also mattered to them how expensive the ride was. And so you can imagine this thinking like, well, I've had 4 beers, but if the Uber is expensive, I'm still going to drive myself home. Whereas the safer people only made decisions based on consumption level. It's like they had a simple rule where they'd say, okay, I have 3 beers and I take an Uber. I don't care how expensive it is. And what was nice is that this decision model was able to kind of nicely slice these two different types of decision makers. And it turns out they were predictive of prior drunk driving behavior or self-reported behavior, which was really interesting. And I think kind of opens the door for this line of research to think about how we can incentivize safer decisions. So for instance, if I know someone really cares about price of the ride, they're very cost sensitive to that, offering them coupons or some sort of discounted ride service could actually influence their decisions and encourage them to make safer decisions, which would be great. And so that's kind of one example of that line of research. My former postdoc mentee, Sarah, we're working on kind of developing even more elaborate mathematical models that will kind of generalize beyond this setting to kind of general risky settings under intoxication. But that's just one sample of work I'm working on in that regard.
It's fascinating because it might actually impact policy decisions or policy implementation on a city, local, or even state or federal level if you can provide kind of a system that really provides folks with an option to potentially take a free ride if they are really intoxicated or something like that to really shift it away from and thereby public safety, basically, right? Increasing public safety. Fascinating. Great.
Exactly, exactly. I think a lot of, you'll see some cities trying to do like free rides on New Year's Eve or things like this. Those sort of programs work. I mean, at least that's what our evidence suggests. It really
Yeah.
can influence. But also it kind of depends on how an individual makes decisions. So, in the future, I think there's a lot of room for trying to, like tailor, you know, interventions to how individuals make decisions. So sort of taking that into account. So I think it's exciting stuff.
Yeah, definitely. So where do you see now that you kind of being or looking at risky behaviors under intoxication or impairment, where do you think your research will be going in the coming years? At the moment, it sounds like you're primarily focusing on alcohol and risky behaviors under the influence of alcohol. Where do you see your research going in the future?
Yeah, kind of multiple arms. So to kind of finish up kind of the addiction thoughts, I'm really interested in working with, my colleagues and my students and mentees in further developing theories of risky decision making that explicitly account for impairment. Now, on the one hand, the models that we're working on are aimed at alcohol impairment, but largely that's because that's sort of the experimental group we have access to, and that's sort of where the substantive expertise of this group lies. But there's no reason to think how we couldn't modify or further develop these models for other types of impairment, which I'm sure would be different. It would lead to different kinds of decision making. But there's lots of substance use out there, unfortunately, and it impacts decision making in often very different ways. So that's kind of like one arm of research I'm looking at and working on. Kind of my other arm of research is a bit more general. It's not addiction driven, but it's more methodological. And I'll be talking about some of this work, during the conference next week, where I'm seeking to help understand how scientists can make better methodological decisions. Now, here's the thing, right? We learn statistics, we learn statistical models, statistical testing, uh, and those are very informative, right? But at the end of the day, humans are making decisions. Like we as human scientists have to make a decision about whether we think evidence is strong, whether we think the evidence is weak, what we do with that information. And so one passion of mine is like, how can we develop statistical tests or talk about statistical evidence in a way that actually informs our decision making? And this kind of goes beyond, you can think of simple Neyman Pearson stuff where, okay, I reject or fail to reject a null hypothesis. That's one level. But another level is like, how should we think about the accuracy of our estimates? How can we understand questions like that? And so some of the work I'll be presenting was recently published this year in Perspectives on Psych Science, looking at how do we interpret estimation accuracy. Now, what I mean by this is like, say, how well do our sample estimates, how well do our sample means even, how well do they estimate the population means that we're trying to estimate? And this is a very general problem in science, right? We collect all this data, and the idea is like we're trying to estimate some difference, right? Or some change across treatment conditions. And, so it's very core to our hypotheses, like how accurate are our estimates? But to really get at that, we need some understanding of what is accuracy. And we don't have good answers for that. So for instance, I may say a confidence interval looks perfectly acceptable, but you, Oliver, could look at that same one and say, I don't know, it looks pretty wide to me. And that's fine. We can have differences. But some of the work I'll be talking about there and some of the work I'm working on developing right now is trying to put a benchmark to that, in that I define a process that is by construction inaccurate. And I think almost all scientists would agree is an inaccurate process. And then I say, well, for estimates to be accurate, they should be distinguishable from this inaccurate process. It's sort of like taking a machine that just gives, comparing the accuracy of a machine to something that gives random garbage or random results. If you can't determine a difference between those two things, then you do not have an accurate device. I'm applying the same sort of reasoning to say our estimates for our models or our estimates for sample means.
That is so because when I usually approach biological phenomena, I always have an assumption, an underlying assumption, which we use in statistical testing, right? That um, this mean and this standard deviation or confidence interval follows a normal distribution.
Right.
That's kind of the underlying assumption. And you just have to increase your sample size enough in order to get a brief enough confidence interval, kind of. That's how I think about it. But I'm also working primarily in the preclinical setting with animals, where we can easily utilize that assumption. Now, and when you talk about accuracy, confidence is kind of tied to that, right? How confident can I actually be in these results? So, yeah, I think we just try to defend whatever our findings are when we talk about the confidence interval or the standard deviation. So but I mean, we make lots of assumptions, right, with that.
Sure, sure. We make lots of assumptions, which is fine. I mean, that's always the mathematical dilemma, right? Like to use mathematics, we have to assume something, which is
Yeah.
likely very wrong. But the purpose of some of this work is like, the one goal I have is like, can we add nuance to some of these conversations? So for instance, along this line of work, my colleagues and I developed this benchmark. And this benchmark it's a hypothetical lab, but you can imagine a lab that also has a control and a treatment condition. And you could have your lab, which runs the control and treatment condition, use sample means to try to determine if there's an effect. Our benchmark is a lab that just generates random conclusions. The direction of the effect is completely randomized. The basic idea is that, what's happening is that the labels on the actual mean estimates are being randomized. So no numbers change, but this lab, this hypothetical random conclusions lab, literally reverses the direction based on a coin flip of the effect. So like whether the drug helps or hurts is determined purely by chance. Now, this sounds like something that would be very noticeable and would generate very inaccurate estimates, and it does. But what's interesting is that for certain small effects and for moderately sized sample sizes, those results will be very difficult to tell apart from standard practice. And we quantify this, and we basically develop a mathematical argument and a statistical tool set around this argument. And I think what the real benefit of this is that one can reject a null hypothesis. That's fine. Maybe your confidence interval, over your effect size doesn't include 0. Okay, that's great. You may have found an effect. What this argument can do is can provide additional nuance to this, is that we cannot say it's quite possible you would not be able to rule out being indistinguishable from this hypothetical random conclusions lab. It provides a very understandable, simple benchmark that people can grasp. And I think that a real benefit of this is that we can say, okay, we have our estimates. We think there's an effect. Let's add some nuance to help us make better scientific decisions. It's quite possible that your estimates may not be all that accurate. And this gives us a way to think about that, talk about it, and quantify it. And which, again, provides nuance to the conclusions. Or maybe your estimates are very accurate and that, outperforming a random conclusions lab is trivially easy. And that's great. But the idea is like, can we provide understandable benchmarks that actually inform our decision making rather than just kind of going by rote or doing a statistical ritual where we say, oh, we rejected the null. Let me tell you all about how my effect is real. Let's add a little bit more contextualization to those questions.
That is something, because we always see the less than 0.05 as the holy grail of significance, but then we know from clinical practice that just because it's significant doesn't necessarily translate into a clinical significant effect. And we often see that with drugs, right? That we do see it has a slight improvement, but does that actually benefit patient outcomes? And similarly, you can do the same for other things, right? So I think that's yeah, I could talk to you for a very long time about this because I think it applies so broadly to so many settings that it could have a huge impact if we actually have like this confidence or accuracy random lab in the background. So to conclude this podcast, what do you see as the main barriers for your research going forward? Where do you see that things might be limiting in regards to carrying out your research?
Barriers, that's a great question. One barrier I think is worth thinking about, and I think can be remedied, and this is often a thrust of like certain T32 grants or things like this, is training. We need more quantitative psychologists. That's just kind of my opinion as a quantitative psychologist, is that we need more of them. And, the training takes time, and that requires money, it requires funding, it requires, amazing students, which we often have a lot of amazing students, but we need pathways for them to develop their skills and time for them to really develop their mathematical expertise. And I think that's a big barrier to research going forward in quantitative psychology. And also just like, getting the work out there and getting people talking about it. But if I could wave a wand, I would like to see more support for training of postdocs, grad students, and kind of better developing these quantitative training pathways moving forward.
Well, I hope that this podcast does at least a little bit to inform folks and get them interested and hooked on mathematical psychology. We will do our part to push this out through this podcast, and I really appreciate you taking the time today to talk to us, Clint.
Thanks so much, Oliver. It was a pleasure.
Thank you all for listening to this U of K podcast, and look out for the next podcast coming your way. Take care, everybody.